out. Okay. I hope it is recording. Okay. So let's say we have this binary tree, and the question is, find a BFS traversal. BFS is level by level. And actually, we want to have the level by level traverse of this tree. Actually, I want to go based on the really basic problem. I know most of, maybe some of you guys, are, this basic problem, but, we need to know and be fluent in the basic problems. And then we can use the basic problems, as a base for all of the, the really complicated problems. So we want to, the question is traverse this binary tree level by level. So one of the, the simplest way is we want to traverse this and then return this array, right? So we'll be 1, 2, 3, 4, 5, 6, 7. And also there's another question. We want to return level by level, all the levels, because the first one, we don't see any level, right? We don't know which, two are, we don't have any idea about the levels. And another way, is to generate this output. And these two, problems are a little different in the implementation, and you will see how we will handle. But first I want to go based on the the first output, which is the simplest and basic, the most basic problem that we use the BFS pattern. So the question is, we have a binary tree, and we want to generate the level by level traverse. In order to solve this problem, actually we need to use one of the really important data structures, which is Q. And Q actually is a first in, first out data structure. What does it mean? It means that, let's say we have a queue here. First, I want to, talk about all the basics, because I don't know the level of, all you guys, I want to try to talk about all the basics, but don't worry, we will be really fast. If you know all of these concepts, the basics, in the second half of the, the session, we will have really, really complicated problems. So when we say, first in, first out, and we name this as a queue, it means that, let's say I have 1 here and add 2, 3, 4, right? So for Q, or, first in, first out, we have, two operators, two operations. One of them is, add or append. And another one is remove, right? Append and remove. So when we append at the end of the queue. When we remove, we have to remove from the first, or from the beginning of the queue. That's why we say first in, first out. And term of queue maybe is different in different programming languages, right? In Python, we have exactly the term of queue, and in other languages you will have a double linked list or linked list, or a double linked list, and maybe you have some other terms. But the thing that you have to be careful, you need to use a data structure with the, the policy of, the strategy of first in and first out. So we want to use a queue to solve, the important part of the BFS algorithm, BFS pattern, is using a queue. And we want to add some, elements in the queue, and then we will pop and we will do some operations, okay? And another important thing, I want to go through this really fast, is the implementation of queue. Actually, in this, when you have this kind of question, you don't need to worry about the implementation of queue. You can assume that you have append and remove, or add and remove functions for queue, and you can write your code. But right now, in order to understand why we are using queue, I want to a little talk about the implementation of queue in different languages. Actually, queue is a kind of, let's say, maybe let's say we want to implement a queue using a linked list, but it is a single linked list. Okay, let's say we have a single linked list like this, and then this is none. So we have append, right? So if we want to append, we want to append at the end of the linked list, right? We want to append here a new node. So what is the time complexity for appending at this, single linked list? Any answer? I don't want to have, really only, if you have any idea, please, share your answers. We want to have more interactive, session.
Can you repeat the question?
So actually, I want to, let's say we have a single linked list, right? It is not double linked list, okay? I want to append a new number in this linked list at the end of this, because the definition of queue, we said, if we want to append, we have to append at the end. And if we want to remove, we have to remove from the first of our queue, right? And right now, the question is, if we have, let's say we want to implement the queue with single linked lists, right? Only one direction. Single linked list means we have only head and we have only one direction, okay? And the question is, if we want to add one node, one item at the end of single linked list, what will be the time complexity?
Order of one. Yeah.
Order of what, because we have only head, right? We have to traverse whole linked list to have access to the end of the linked list and add. So it is order of n, because we have only single linked list, right? And we have access only the head of the linked list, right? If we have, single linked list. Okay, but if we want to remove from the beginning, we can remove this only with order of one, right? This is, the add, and this is remove. Because in the single linked list, we have access only the head of the linked list. So that's why if we want to add at the end of linked list, we have to traverse whole linked list to be able to add a new item at the end. Okay, does it make sense? Okay, so in order to, but we don't want to have order of n for adding. We want to have order of one for both operations. Actually, the objective is to have order of one for both of these guys. Okay, so if we want to have order of one, so single linked list is not enough. So that's why we use double linked lists. Double linked list means also we have tail. We have access to the end of the linked list, and also we have some, backward, opposite directions, right? And if we have tail also, definitely order of one will be also for add function. So that's why in all the programming languages, if we want to define a queue, we have to be careful. It should be double linked lists. In Python, if we use queue, because we know that it is double linked lists. If you use single linked list, it will work, right? But when you are writing that add, it is order of n, and your time complexity will go higher, right? And in the interviews, you have to be careful. If you are using some built-ins, you have to be aware of the time complexity of all of the operations, all of the functions that you are calling for that built-in data structure. But in any language you are working, you need to know how to implement how to use the queue, stack, and all of these guys. So this is one of the really important topics. You have to know why we are using queue. The philosophy of the queue is because the order of adding and removing, both of them are done based on with the order of one. So we don't cost any extra time complexity. Okay, so what is the idea? Why we are using the queue? Let me do this a little faster. Do you have any question on it so far? Okay, let me check even the text message. Maybe some people asking the text. Where's the chat? Okay. Okay, we don't have any question. But please, if you have question, unmute yourself and ask your questions. And okay, so let's say, again, I want to, write here, the tree. And why we want to use, the queue. Let's say we have this queue and initially it is empty. I want to add the root value here. I will add 1 here. In the next round, I want to pop 1 and add all of its kids, which is 2 and 3. I will have 2 and 3 here, right? And because I popped this, I want to add this in the, let me use the red color. Whenever I pop, I will add this in the output. 1 in the output. And the next round, again, I want to pop 2. I will, have 2 here. And I will append the kids of, 3, which is 4 and 5. And again, in the next round, I will pop 3. I will add in the output. And I will push, or add, its children. And I will pop 4. There is no children, so I don't have any, adding, add operation. I will pop 5. I don't have any add operation. I will pop 6. I will pop 7, and it's done. Whenever the queue, we started queue with 1 element, the root value, and whenever the queue is empty, we are done, and we can return this as in the BFS or level by level. Actually, it's not level by level. It is BFS unit traversal. Because level by level is the second, this guy. The level by level is, this one, because we see the levels. Actually, when we talk about, 1, 2, 3, 4, 5, it is level by level, but, we don't know the levels actually here. Okay, so let's implement this first solution, and then we will go and change this to have the second output, which is the level by level, this guy. And then we will go and use this BFS pattern to solve more complicated problems in the grids. And the reason I've selected the grid problems for today's meetup, it is really common and popular, the grid problems, especially if you are doing the on-site interview. In phone interview, usually, the interviewers don't go over, the graphs or grid problems. Usually they, at most they ask you, the binary tree. And most of the time, more than 80%, they ask, about the arrays, strings, and linked lists, and at most, binary tree. They don't go over, the grids and the graphs. But the on-site really interviewers, really they love to add, they love to ask, the grid problems and graph problems, because they are really visual and they are really interesting for interviewers. Okay, so that's why today my main purpose is to solve some grid and graph problems. But before going over that, I want to have the basic BFS, and then we will extend the basic BFS, and you will see how we are using the pattern. I want to show you the power of the using problem solver patterns to solve, tens of problems. Okay, so right now, as you can see, we need a queue, and at first we will add, the root in the queue. And then we will inside a while loop. So let's me write, the whole, picture. So we have a queue, and we will add. So we will define a queue. We will add first element in queue, which is initialization. But here it is root, right? And then we will have a while loop, while in a queue. It means while queue means while queue has any elements. And inside of the while, we will pop first element, because we want to have the first in, first out. The first element we are assuming is the first element we added. We will pop this, and then the second step, we will update the output. And this third step, we will push. Actually, we use push and pop for stack. The terms of push and pop we use most of the time for stack. And let me follow the so actually we will remove this guy and add the children in the queue. And this is the whole structure. You have to be really fluent. It seems easy, but you should be fluent and fast in developing even the basic algorithms. This is one of the, again, another mistakes I saw lots of people do. They don't practice even the basic problems. You have to be really fast in developing even the basic BFS. If you are not fast in implementing it, because for interviews, knowing is not enough. If you know the solution, you should be fast enough. And in order to be fast enough, you should be fast enough in the basic algorithms first, and then you can be fast in the advanced and complicated problems. So this is the whole structure of our BFS. We define a queue at the first element in this scenario, in this problem is root, and then in while queue we will go and remove first element, update the output, and add the children, and we will go until we finish the queue. So let me write the code for this part. So first of all, let's define our class for tree node. So because here we have, and most of the time in the interview you don't need to define the class for for example, if you are implementing the BFS for binary tree, you can assume that you have a binary tree. But right now, I want to do this because it doesn't take, it will be only in the 10 seconds to define, that class. Actually, I'm using, I forgot to say, you guys, I'm using Python in, my classes because if you are a Python programmer, that would be nice for you. And even if you are not Python programmer, Python code is really readable, and it can be really, as a pseudocode for the other guys. If you are doing Java or C++, it is not really complicated. I'm doing really simple Python. I'm not doing one-liner, the Python. To be in that way, all you guys will be able to read the code. So init is our constructor, and in constructor for each tree node. For tree node, we have a value and left and right pointers, right? So that's why we'll have self, that's val, will be val, and self that left will be none initially, and self that's right is none. Let's assume we have this class and we have created a tree and we have access to the root of the tree. Let's say if we have this, binary tree, and we have access to the root of this guy, and the left and right, and each node has left and right. If they are leaf, they don't have the left and right is none. So let's go and define, our function. I don't want to define inside of the class. Sorry? Go ahead. Go ahead. Excuse me, we can't hear you. Do you have any question?
Hello?
Hello, do you have any question?
Oh, no, sorry, my line was, there was a minor accident here and my line got unmuted. Sorry, go ahead, guys. Sorry about that.
Okay, no problem. Let me, okay. Okay, let's go. So let's go and define our BFS traversal, right? So let's say I want to write BFS traverse. You want to define a function for BFS, and the input is root. We have only the root of the, our, tree. First of all, I want to define the results, which is an array, or in Python we say list. But when I say list in Python, it is exactly equivalent to vector in C++ and in Java. Okay, so we have a result, and first of all, let's check if root is none. So we have to return, the result which is empty right now. This is only, the sum, checking some, base cases, right? And I said, the first step is defining a queue, right? We want to define a queue. And in Python, in order to define a queue, we need to use the dequeue. So you have to import from collections dequeue. Dequeue is a double linked list. It's a double linked list, and we want to define a double linked list here. And so I will write queue is equal to dequeue. So this is definition of the queue definition, right? Queue, actually declaration. Okay, so the second step is we need to add first element in the queue, right? So I will write queue that append root. What is the first element is root. So we want to append inside of the queue the first element, and then we will go over the while queue. When I'm writing while queue, it is exactly equivalent to the the sharp hashes for comments in the Python. Actually, I'm writing some explanations in the comment part. While queue, it means while len of the queue is greater than. I can write this also, but while queue is really simpler. That's why I'm using only while queue. So inside of the while queue, what is the first step? It is remove the first element from the beginning. You have to know all the data structures in your language. So I know that if I wanna remove from the first of the dequeue, I have to use pop left function. So the first thing we have to do is the current node is equal to queue dot pop left. Pop left means if we have a queue like this, let's say we have one here, pop left is pop from left, is pop from the beginning. So right now the current node is my the popped version, right? What is the next element? Next step, update the outputs. Right now the current node, I need to add this in the results. So let's say I have the result here, and it is empty at first, right? So right now I want to append in the results. I will write result that append current node, but we don't need, we don't want to add object inside of the, because we know the current node is a node tree like this, we defined in the class, right? This is current node is an object of the class tree node. We want to add only the value of that, this node. So we'll write current node dot val. Okay. So we appended one here. Let me erase this guy because we want to add all of the guys. Okay. So we appended. Right now it's time to add the next elements. What is the next elements in this problem? The next elements are the left kid and right kid. So I will check, and the order is really important because we have to add left kid first, right? Because we want to have this order. You cannot add, the first right in the right node. You have to be careful about the assumptions. So that's why we have to add the current node that left in the queue and also the current node that's right. But before adding, we have to check if they are not none, we need to add them, right? If they are, let's say we are in over, this node, 1, 2, 3, 4. Let's say we are in the 4 node. We don't have any kid for this 4. So we don't need to add none in the queue, because if we add none in the queue, we will have an infinite loop. Queue will not be empty. Okay, so that's why we have to check if current node dot left is not none. So you don't need to write is not none in Python. It means, if current node dot left, it means if this is not none. Okay. it means, we have a valid, current node that left. If we have this, we have to append q dot append current node dot left. In the same way, we have to write, if current node dot right, we have to append q dot append current node dot right. So we will do this because we don't add whenever we don't have any q will be empty at the end. So right now we will do 1 as I did, in the first, the solution. 2 and 3 will be added, and then we will pop this, 4 and 5 will be added, and in the same way. Okay. At the end, q will be empty, and every time we pop, we append this in the results. At the end, after we doing this while loop, we will return result. Okay, so this is the most basic, problem that we can have for BFS. The reason I did this, I know for most of you guys, maybe it is repetitive, but again, I'm saying, you have to be able to implement this in only 2 minutes, in 3 minutes, right? If you're already fast enough, you will be able to figure out, the really more complicated, problems. As you can see, we use a queue, and what is the time complexity? Let me talk about the time complexity. We only meet any node only once, right? In the code, as you can see, we meet any node only for one time. It means that the order time complexity is order of n. And also we use a queue for a space complexity. We use a queue and we push all of the nodes in the queue. So it means that the space complexity also is order of n. And actually this is the optimal way to have the BFS traverse for a tree. As you can see, again, I wanna show the structure here. This part is adding next elements. I'm saying next because depending on the problem, next element will be changed. Here, next element is children. In the grid, we will have next elements will be neighbors. And in graph also will be our neighbors. Depending on the problem, the next elements will be changed. And actually here, exactly is, the pop part, right? This is the popping pop actually, and also we will have again another part that's updating the results. Again, you will see in the next problems, this updating part will be maybe more complicated, not like this. And at first, you will have the initialization of the queue. Queue. Okay. This is, the whole, structure for, the BFS, actually the simplest BFS, but it is really common and popular in the coding interviews. We have, but, anyhow, do you have any question about this, basic problem?